Hello again everyone. This is our second demonstration video regarding the commercial finite element software SAP2000. This video we're going to use SAP in modeling a one-dimensional bar problem considering the example shown in figure where you have a bar, its length is 5 meters and it is subjected to a linearly varying axial force which is acting along the positive x direction. So x here is the global coordinate system along the center line of the element, and the displacement associated with this direction is u. So the load is varying linearly, so you have linear variation, and is defined by the function q as function of x, where q as function of x equal to 3000x. So the load is varying from 0 at node 1, because at x equals 0 the load is 0, and at node 2 you have the maximum value of the load, which is 15,000 kilonewton per meter. As you can see here, node 1 is restrained, so it's prevented from translation, which is u1 is equal to 0, while at node 2 you have the bar is attached to a linear spring, linear translational spring, and the stiffness of the spring is 4,000 kilonewton per meter. The cross-sectional area of the bar is 0.125 meters square, and the material here we are assuming the bar is steel, so E steel is 2 times 10 power 5 megapascal. As we discussed in the first video, in video number 1, that in SAP2000 there is no bar element, so we used a 3D frame element which has 6 degrees of freedom per node, and we reduced this high order element by deactivating all degrees of freedom except the translation along x. So we reduced it from 3D frame element to one-dimensional element to simulate the bar. So this means that we are using a high order element to simulate a very simple problem, as you can see. So that's why in SAP for this problem I'm gonna model the entire bar using one element only, which is element 1 connecting node 1 and node 2. And I'm expecting that this solution, even without dividing the element into small divisions, we're going to end up with the exact solution. So based on our engineering judgment here and our understanding of the problem, that since the bar is subjected to a linear variation of the axial force, we are expecting that from exact solution we should end up with quadratic here means second order variation in axial stresses. Like for example, if we try to simulate that, this node is restrained, so I'm expecting to have, since the load is acting along positive x, so the body will be under tensile stresses, so I'm expecting to have here the maximum tensile stress, because the maximum tensile stress will happen at the node where you are preventing translation, and then this tensile stress will start to decay but quadratically until it reaches almost zero somewhere, and then go a little bit reverse in sign to have negative, which is compression stresses, and this is due to what? Due to the compression force in the spring. So this spring will apply compression force here because the bar is trying to deform and the spring is preventing it, so you'll end up with very small, or whatever the value we don't know yet, so you'll have tensile stresses along the length of the bar, but close to the end of the bar you'll end up with compressive stresses. So we'll see what are the values that are coming from SAP, but we have a kind of initial prediction what we are expecting as outcome from SAP. So this is compressive stresses. Now the trick here, how are we going to simulate the spring? That's the question. So how are we going to simulate the spring which is attached at node 2? Let me take a copy of this figure because we need to explain how we're going to do that. So actually in this demonstration I'm gonna show you how we're gonna define the spring using two approaches. Approach 1, we call it joint spring. Okay, so joint spring means what? You're gonna model the bar, using a frame element which we're going to reduce it to simulate the bar, connecting from node 1 to node 2 as a line element. By the way, in SAP we always model the element through the center line of the cross section as line element. So this will connect node 1 to node 2 as we did before. And then we'll go at node 2 and define a spring at this joint, and this spring should be along X or locally along 1. We defined before the local axis, so it will be along local 1. So this is one approach to define K. The second approach that I'm going to cover, which is called link element. And under link element we have different things, which is linear spring, nonlinear spring, gap element, but our focus is linear spring. And we're going to see how to do that. The main idea is what? The main idea is that we can even simulate exactly this problem. Like this will be a bar connecting node 1 and node 2, and you can create a new node, let's call it 3, where the distance between node 2 and node 3, I will call this distance user defined. User defined means what? That you can decide about this distance. You can take it 1 meter, 2 meters, whatever, but don't take it too high. Like I think 1 or 2 meter is reasonable, because the distance will not affect the stiffness of the spring. It's a link. The most important thing that you define the value of K. So we're going to simulate what we call 2-node link, which is connecting node 2 and node 3, and we're going to see how to do that. So in order to model the bar, first step you need to decide about the geometry. So as we agreed that we need to start with grid lines, so I will start with the first approach. In the first approach we need grid lines here along node 1 and node 2. That's it, because this spring will be simulated at the node. So I will say this grid line A and this grid line B, where the distance is 5. So that's very easy, straightforward step, and we can do quickly. So let's start with this approach in SAP. So I will go to SAP now. So we're going to start with a new file. Again, we decide about the units. We'll go with kilonewton and meter, and again we'll use the grid only case from the template. We need 2 grid lines in X. So we need 2 grid lines in X direction. Since it's a one-dimensional problem, I need only 1 grid line in Z, right? And by default you can also do 1 grid line in Y. So what we worry about is the X direction. The spacing between the 2 grid lines in X, it's 5 meters. And as we agreed, you have by default the minimum spacing in Y. It has to be 1. You cannot provide 0. Like if you try 0, it will tell you it cannot be 0 or negative. So although we don't need grid lines along Y direction or Z direction, you have to make it the default, which is 1. Finally, by default, the first grid line location, you want to have it at the origin, which is okay. I will keep it as is. As usual, you have 2 view windows here, so we're going to get rid of one of them, and then we always set our view to XZ view. So I will start now. This is a kind of review to video number 1. We start again. First thing that we have to define the materials. So our material, I will add new material and go and define my new material as user defined. We'll go with steel. What I need to make sure about is the value of Young's modulus. So either you change this to 2. By the way, the units here is kilonewton and meter. So either you make sure that you have the right conversions of the units. If you are not sure, you can go write it as whatever you have in your problem, which is 2E, which is times 10 power 5. 2E5 means 2 times 10 power 5. And then you have the units that you have is megapascal. Right away, SAP will do the conversion for you. It's a one-dimensional problem, so we don't need to define Poisson's ratio. Don't worry about that. Anyways, the black box will not take this value. We are not considering the own weight, so again, don't worry about this as well. We are not doing any kind of thermal analysis, so there is no need to worry about thermal expansion. Also, we are not considering design, so we don't worry about the properties of steel material in terms of yield stress or tensile stress and ultimate stress. So we are done. We are naming the material steel, so remember that name because we're gonna link it to the cross section that we're gonna define in the next step. So next step, we define section properties. We agreed there is nothing called bar element here. What we have is frame section. So I'm going to define frame section, add new property. By the way, if you look here, you have the area, it's 0.125. So one way to do it, you can come up with equivalent diameter of a circle, of a cross-sectional area in the form, it has a circular shape, which will give you this area, which is 0.125. But again, there is no need to do that if you would like to use this circular section. There is no need for that because we have already a very powerful tool, which is SAP. So I can go and define a general section that I can provide the area right away. So in this section, I'm going to provide the area here, which is 0.125 meter square. My units is in meter. Make sure always that you follow the correct units. And we're going to name this section, let's say bar. We have to link this cross section to the right material, which is steel that we defined in the previous step, and double check that you have the section properties correct. As we agreed, we don't need to talk about set modifiers or section modifiers now, and time dependent properties, that's not relevant to our problem. So now we are good. So I'm gonna go and start drawing the frame element. So we're gonna draw the frame element, which is straight frame element. The section is bar connecting from node 1 to node 2. And we are good. We are happy with that. And we are modeling the entire problem with one element. Now we need to go define the load patterns. Again, by default, you have the dead load. We will not run this case. I will define a new case. Let's call it distributed axial. And it is under other. It's not live load, roof load, wind. So for now, it's other. I'm not considering on weight, so the self weight multiplier is 0. And I'm going to add this, define this as a new case of loading for me. So we're going to assign the load. So I'm going to choose the element and then go assign the frame load, distributed load. We did that previously in video number 1. I'm going to assign it for the case distributed axial force, and either in the global direction, which is X. So we agreed that I'm going to define the load. It's linear, varying between two nodes. So I need only node 1 and node 2, let's per se, which is the relative distance along the length of the element. So this value here should be 0. And this value should be 0 to eliminate nodes 3 and 4. Because you can define more than two nodes if you have more complex loading. So at 0, the load is 0. Like at relative distance 0, the load is 0, which is at the node number 1. At the end of element 1, which is at relative distance 1, your load, it has to be 15,000 kilonewton per meter. So I'm going to apply this. By the way, if you do any mistake, you can always go with delete existing load, choose the element, apply, is going to delete the load right away. But now we're going to go back. You can add or replace. Be careful. Adding, it means if you have already load on the element, you might duplicate the load. So you might be careful. So it's better to use replace to make sure that you are replacing anything existing. So I'm going to choose the element again and apply. So now we are good in terms of loading. Now so far we did define the material, the cross-sectional area like E and A. L is coming from the geometry, so the stiffness is ready. The load vector is defined through the load. We need to assign the boundary condition. So make sure first let's go to do this step that I'm gonna go define from set analysis options that it's not 3D analysis, it is 2D. So I'm getting rid of 3 degrees of freedom already. Also, it is a bar element, so I don't need transverse or vertical deflection. I don't need also rotation about Y. where y here is the coordinate, is the direction of the axis which is perpendicular to xz plane. So I need only translation in x. So now we reduced the element from, it's two steps. It was previously 3D, it was 3D frame element. Just clicking xz plane, you are reducing the element from 3D frame to 2D frame. And now by removing uz and ry, this means that we are dealing with a unidimensional bar element. Now I want to restrain this node, so I will choose the node and then assign joint restraint, and I'm going to restrain direction 1 as we agreed. The local coordinates for the joint 1 is always in the direction of x. If you are confused at any point, go set display options and you can activate the local axis for the joint and the local axis for the frame, and then you can view that in 3D. So we have the red for the joint is 1, then you have 2 out of plane and 3 is vertical. Here for the frame you have 1 in red, that's 2 in green, and the 3 following the right hand rule. So let's deactivate that, just not to confuse you with the local axes. Now I'm gonna model the spring using approach number 1, which is very straightforward. Approach number 1, that I have a spring attached to this node. So I'm gonna choose this node. Again, let me explain this. The spring is attached to the joint, so I will show only the local axis of the joint. The local axis of the joint, you need a spring in which direction? That's the question. You have local 1 along the center line of the element, then you have local 2, which is green, perpendicular, out of plane, and the vertical 1, that's local 3. For our problem, for sure, you need your spring in the direction locally 1. So that's why if you choose the joint and go assign joint, as you can see here, springs. So we'll go with simple spring. It is either local or global. So I will go with local in direction translation 1. You can add also you can add rotational spring, but our problem that we have translational spring, and you need to define here the stiffness of the spring, which is 4000 kilonewton per meter. So I'm going to define here this value, 4000 kilonewton per meter, and apply. So as you can see, let's zoom here, it's adding a spring, and automatically SAP added the joint spring and applied the boundary condition, because the spring, if you are not fixing it from other direction, I'm not sure if you can see that, it applied boundary condition right away. So it's a kind of automatically assigning a spring to this joint and then boundary condition on the other side to make sure that you have a kind of stability in your structure. Equilibrium within the spring. So now we can go and set the load cases that we will run. We don't need to run, no need to run dead load and no need to run model. So I will run the case which is distributed axial force. Definitely if you click run now, it will ask you to save the file. So I'm gonna save it, let's say example 3, and let's call it example 3 but with a spring now. So now the program is running. So let's show the nodes. If you start the animation of the deflected shape, it seems that under the distributed axial force which you are expecting, the bar is going to elongate. The spring is trying to prevent this elongation, but it seems that the stiffness of the spring is very low compared to the load. So if we stop the animation, we can hover here and click and check the displacement. The displacement at this free end, based on what we have in terms of the relative stiffness between the spring and the bar, we have around 5 millimeter. If you would like to plot the reactions for this case of loading, again, you go to show forces and stresses, joints, and then if you click OK or apply, you're gonna see that, by the way, this one 19.98, that's the force in the spring, while this one here, that's the reaction, the support reaction, which is the coming from the load acting on the bar. So you can get a kind of feeling about the relative stiffness between the spring and the bar. Also, we can go here and check the stresses or axial forces. I will go with the stresses S11 and apply. And as expected, we are expecting quadratic variation in the stress. So let me hover on the element and then right click. So in megapascal, which is Newton millimeter, at the maximum stress is at distance 0, where the point that you are preventing translation at the support, you have around 300 or 299.8 megapascal. And this stress starts to decay. It's all tensile stresses because the bar is under tension until it reaches so close to the spring, and as you can see, the stress reverses and you have negative 0.16 Newton per millimeter square, and this is due to the force, the compressive force coming from the spring. You can also show forces, and here this will tell you right away in kilonewton. This figure shows you reaction and the distribution of axial force. This one, as you can see here, if you go to the far end at 5 meters, it will give you right away the force in the spring, which is applied as a compression force on the bar. So by that we reach approach number 1. So I'm gonna go unlock the model. This is unlock when you run the model, it's locked. Like you can only because you are in the post-processor mode, like you cannot change anything, because changing that's pre-processor. Now we are dealing with post-processor, which is showing internal forces and stresses. So I'm going to unlock the model again, so to start doing another approach in defining the spring. So the second approach, which I'm going to use a link element. To save time, what I'm going to do, I'm going to select the entire problem, which is the bar that we modeled, including the axial force, the loading, and everything. And I'm going to replicate everything vertically. So I would like to have another copy of this bar with the load acting on it, with everything, like replicating it along that direction, but let's say with distance, since it is below, so I would say negative, let's say -2 for now. And I need one copy. So now we have the same problem in the same interface, okay? But now I'm not happy with the joint spring in this case, so I'm gonna go choose this joint, and I'm gonna delete this spring, as if you are assigning a spring, but instead of assigning a spring, you're gonna delete the spring. So now I'm deleting it, okay? So this point now is free. To check about the effect of the spring before we model it in a different way, let's do another run. So I'm going to run the model again. So let's check the deformed shape. That's number 1. So as you can see, the behavior didn't change in terms of the deformed shape, but the value of deformation I'm expecting to have a kind of very small effect of the spring, because the stiffness of the spring is very small. What's going to change if you plot the axial force distribution? So the axial force distribution in this case, when you remove the spring, if you go to 5, the force here, axial force is 0, almost 0. And you have the entire force acting on the bar, the reaction is 37,500. So the entire load goes to this support. If you remember, there was very small part, which is around 20 kilonewton taken by the spring. So definitely the spring stiffness here, it's very flexible. So if we increase the stiffness of the spring, this will distribute the load relative to the stiffness. So I will unlock the model again, because definitely that's incorrect. It's not modeling our problem. I was just explaining the effect of the spring. And we're going to see now how can we model the spring using link element. So link element, it has to be between two nodes. So I'm going to choose this node and replicate it this time along x. So make sure that this is back to 0. So z is 0. And let's assume that the length of this link is 1 meter. So now I replicated or created a node which is at distance 1 meter from node number 2. Now I'm going to go define. In section properties, there is something called link or support properties. So I'm going to go here, add new property. You have different options. That's another topic which it's worth like one video, separate video to talk about link element. But for now, we'll choose the first choice, which is linear link element. I will call it spring because we are dealing with linear translational linear spring. So I will call this one spring for now. And we need to define what type of spring is this. First of all, is it linear translational spring? Is the direction is used, or is it rotation? Definitely it's translation. So our focus is either U1, U2, or U3. So 1, 2, or 3, this depends on the local axis of this link element. So what I'm going to do now is defining U1, and then we'll do a check if our assumption is correct or not. So U1, and then we're going to go modify and define the stiffness along this direction, which is 4,000 kilonewton per meter. So that's our stiffness in direction 1. That's, I'm assuming that direction 1 is the longitudinal direction of this link element. And we'll check if what we are doing here is correct or not. Because you have to make sure always that you are defining your stiffness in the correct direction. So now I'm going to go draw two joint link, and this link, which is a spring, if you have another one, you can switch different link elements, but we have only one. So I'm going to go define this link element from here to here. As you can see, it gave you a spring which is connecting node 2 and node 3. Don't forget, we define the stiffness along U1. So let's make sure that this is correct. So I'm going to go again here, display options. Under links, you can show the local axis of this link. So as you can see, now it is showing, I will show 3D view. It is showing for this element, which is the link element, 1 is red, that's 2 in green, and that's 3. So now I'm confident that when I defined U1 direction, the stiffness is 4,000, that's correct. So now we are good, and we can get rid of the local axis here. If you forget and start running the analysis now, this will give you the same as if there is no spring, because this node is not prevented from translation. Like it will give you the same thing as we did in the previous run when we ignored the effect of the spring. So that's why I have to go and check this node or choose this node and assign joint restraints and prevent it from translation along one direction. So now I'm holding this point. This means this spring is going to contribute now to the stiffness, to the global stiffness matrix in our problem. So now the question, when I replicated the element from here to here, how can I make sure that the load is also replicated? If you at any certain point you want to check, you can go two ways to do that. To choose the element and then right click, it will give you all the information about the element. So you can go to loads. It's telling you that this element has a load which is 4 sprint length. At the start it is 0, and at the end it is 15,000. Another way to do that, you can visualize that actually. You can show element assigned load frame. Sorry, it's not this one. It is the other one. Display element load. Just this message, click yes. So choose the case of loading that you would like to show the load, and then OK or apply. It's going to show you the load, and here is showing the load in both cases. So now we can run our model. So let's compare first the deformed shape. So as you can see, they have the same deformed shape, and even the spring is elongating and shortening with the animation. You have the same displacement, which is 5 millimeters in both. What's our judgment? Because the stiffness is very low, we cannot judge based on the displacement. We have to judge on the stresses, or let's check the joint reactions first. So as you can see here, you have the same support reaction at the bar and the same spring forces. So although we are using two different modeling techniques, we ended up here, as you can see, the same straining actions and same internal forces in the spring. Also, if you show again the frame, the axial forces or the axial stress distribution in the bar, so we are expecting, if we show values even this time, we are expecting to have the same values identical. And this concludes this video, that we modeled a bar which is attached to a linear translational spring using two different approaches. Approach number one, here we used what we call joint spring. Approach number two, we used what we call a two-node link element, where we defined the direction of this link element, the stiffness in direction 1, based on the value of the stiffness that we have. By this we conclude video number 2, and thank you so much. I hope this helps you to model one-dimensional bar problems. Thank you.